Hello, everybody. Section 4.3 is one of the most important sections in differential calculus. We are going to be talking about maximum and minimum points of a function. The plural forms for those words are maxima and minima. We'll talk about that in just a second, okay? But take a look at this surface behind me. You see the orange surface? It seems to just kind of go way down to infinity. You can tell that that surface really doesn't have any minimum, right? Because it goes down to infinity. It doesn't even have a maximum because it seems to go up to the infinity. So not every function has a maximum point or a minimum point, okay? But what do we mean by those words? Okay, it turns out to be very, very mathematically important to define those terms carefully, all right? So first, we will define what we mean by maximum and minimum points, and we'll have different types of them. And then we'll decide how to find those things using calculus. Okay, so prepare for this very important section as we study section 4.3, maxima and minima. All right, as we talk about optimization, right, we have the word maximum, which represents, the largest or highest value, right? When you have a maximum, that's the highest point. The lowest point is often called the minimum, and both of these together are called an extremum, M-U-M, right? Okay, so that's what we mean by an extremum is either a maximum or a minimum. Now, if you have more than one maximum, then the plural, official plural form of that is maxima, sort of like a car from a certain Japanese manufacturer. The plural of a minimum is minima. Sorry, it's Latin. And then if you have more than one, it's called an extrema, right? MA ending for all of these, right? So we'll be using these terms. Don't be confused by the strange plural endings of these words. Okay, so I have 7 blank graph papers here, right? So let's say when you have something like this, okay, that looks like a parabola, right? Y is equal, this is the origin, y is equal to x squared. All right, do you see a maximum or minimum point if it's defined on all of the functions, all of the reals? Okay, we'll come back to that. What happens if you have x cubed? So something like this. Okay, how about a sine function, which will be like this, of course, right? Goes up to, goes up to 1, down there, down to 1, -1, up to 1, and so on. Think of, where you would identify as maximum and or minimum point. Okay. How about x cubed, but restricted to -1 to 1? So this will be something like this, where it ends at -1, 1, -1, and +1, comma 1. Right, so this is called a restricted function because the domain is restricted. Okay, it's not the case with the first 3 functions. That's number 4. Number 5. How about x cubed once again? Except now it's restricted on the open interval from -1 to +1. So the graph will be going like this, and there's a open end on both ends, open circle on both ends, like this. Okay, and then number 6, you may have a function that looks like this. I'll go through this. All right, so what is that? This is a function x cubed plus 2x squared minus 4x. Okay, so it's a typical cubic function with ups and downs. All right, and then number 7, this is something we've seen before, but y is equal to x to the 2/3 power. All right, I want you to look at all of these 7 functions. We are going to be talking about maximum and minimum points. Now, for each of these, I want you to sort of maybe pause this video and tell me where you think the maximum and minimum should be, okay? And think about how you define these words, because again, the definitions will actually be quite important, Okay, I mean, it is important from mathematical standpoints as well as from applicational standpoints. All right, so think of what you would call, what points you would identify as a maximum point or a minimum point, and together extreme points or extremum points. All right, so what do you think? Okay, I'm going to write maybe our thoughts in blue here. All right, this point, is that minimum? I think most of you would identify that point as a minimum because it certainly looks like the lowest point on the graph, right? And you would be right, this is called a minimum. It turns out we have, we'll have to distinguish a couple of types of maxima and minima and extrema. This in terms, this is actually called an absolute minimum point because it is the lowest point in the entire domain. It's also called a local or relative minimum point because it is the lowest point in an interval containing that. Okay. All right. So how about this? Does this number 2, does this have a maximum or minimum? Well, it goes to positive infinity and goes down to negative infinity. So maybe we can say infinity is the maximum value. No, you don't want to say that, okay? Because again, number 1, infinity is not a number. And number 2, whatever you say is maximum, I can go beyond that, right? So there is no maximum or minimum. So I think we can safely say there's no max, no minimum, no important points here. Or is there, okay? I mean, this certainly may be an important point, 0, because something may happen at that point. The derivative, for instance, at that point is 0. Does that make any difference? These are the questions that we will be addressing, so keep these in mind. Sine function, there is a maximum point, right? And there is a minimum point. There's another minimum point, okay? So the maximum point, there seems to be a whole bunch of them. In fact, the sine of x is defined for the entire real number line, and this maximum is pi over 2. There's another maximum that occurs at 5 pi over 2 and 9 pi over 2 and all that. So there are infinitely many points of what we call the maximum, okay? And same for minimum. So some functions seem to have infinitely many maximum and minimum points. Now, do we call the x value maximum or y value maximum? Okay. Well, to give you the simple explanation, when we talk about the maximum value, we are talking about the x value, sorry, the y value. So you could safely say that the maximum value for the sine function over all the reals, all the real numbers, is going to be 1, and the minimum value is -1. But they happen to occur at infinitely many points, right? And we'll come back and discuss all that, all right? How about this restriction? X cubed restricted to -1 to +1. Okay, so with this restriction, this is clearly the maximum point. So you can say the maximum occurs at the absolute maximum. The highest point occurs at when x is equal to 1 and the value is equal to 1. The lowest point, the absolute minimum, occurs at -1 and the absolute minimum value is -1. Okay, and each of these occurs exactly once. And so that seems to be okay. Even though the derivative at this point is not 0. See, the thing is, these maximum points here, the tangent line seems to be horizontal, meaning that the derivative is equal to 0. Now here, the derivative is definitely not equal to 0, but we are calling them maximum and minimum. So what is going on? I mean, do we have to worry about the derivative? Yes, we will, but not yet. Okay. What happens if you have an open interval? Isn't that the same thing? I mean, this point is 1, 1, and so you could say the maximum is 1, and the minimum is -1, occurring at -1. Okay. Well, you could if the points are filled in, right? But look, you have a hard time. I think you should have a hard time saying that the maximum point is 1, or the maximum value is 1, because there is no point in this open interval. Remember, the endpoints are not included. In this open interval, the value of the function is never equal to 1. Now, it gets very, very, very close to 1, but it'll never get to it, right? So in other words, there is a point where x cubed is going to be 0.9999. but it'll never become exactly 1. So here we will say there is no maximum or there's no minimum. Is that right? I mean, does it sound very strange, doesn't it? Yeah, it does sound strange, but mathematically it is right to say that there is no absolute maximum or minimum for this function on an open interval from -1 to +1, because again, the function never gets up to 1 or down to -1. All right, so how about number 6? This is an interesting function because it seems like there is a maximum point here, except it's not maximum because the function keeps going up to infinity. In this point, looks like it's a minimum point, but it's not the lowest point because it goes down to -infinity elsewhere, right? So we need to have a new name for these places because these phenomena, of course, occur often, right, in smooth curves. So we're going to give a new name for these. These are called local or relative maximum. We will define these carefully. And this is also a local minimum or relative minimum. Okay. The word relative is used as in opposition to the absolute. Absolute and relative are antonyms. Local is probably a better description of what's happening. But anyway, these are not absolute maximum and minimum. These are local extrema. Finally, we have x to the 2/3 power. This is an even function. There is a sharp point here. Sharp point? Yeah, the function is not differentiable at this point. But can we still call this a local minimum or absolute minimum? Yeah, so it seems like we would want to call this a minimum because this is the absolutely lowest point, right? And in fact, it's both an absolute and the relative minimum. And we will describe again, once we have the definitions carefully stated, then you will be able to determine if these are absolute or relative minimum. All right, so with all of these, I hope you can figure out or you have some idea of why it's important to define these terms carefully, okay? Just because some point looks like it's the highest point, or if there's an open circle, we don't know, we can't really tell you if it's a maximum or minimum unless we have a precise mathematical definition, okay? So this is the background that's going to lead us to some of the most important definitions in our calculus class. All right, so here's the first definition. Let's say if f, and by the way, f doesn't have to be differential, right? We haven't talked about, well, we talked about how this has a sharp corner, which makes this function not differentiable at 0, but you can still talk about maximum and minimum independent of differentiability. So if we don't assume f is differentiable, if f is defined on any interval, and it could be the entire real, that would be the interval from negative to positive infinity, right? Typically, this interval is the entire, doesn't have to be the entire real number system. It could be just an entire domain of the function, okay? If f is defined on an interval I, then we say f has an absolute maximum at C if f of C is greater than or equal to f of A for all x in I. What in the world is that? I should also say, and f of C, the y value, is the absolute maximum. Absolute maximum. So make a clear distinction here. The absolute maximum refers to the y value, which is the highest point of the graph, okay? But we say f, the function has an absolute maximum at this point. So if the question says, where does f have an absolute maximum? Then you could say, the x point, the x value, which is C. If you are asked to find the absolute maximum or absolute maximum value, then you give the y value at that point. All right, now the picture is, of course, you could imagine if you have a function like this. Let's say here's a function, and this is your interval I. All right, this is the point of the absolute maximum. You can say the absolute maximum occurs at this point C, because f of C is higher than or greater than or equal to any other value of fx, where x goes from, ranges over the entire I. Now, this is not an absolute maximum because there's a higher point, but this is where absolute minimum occurs, right? Which we have to define. F has an absolute minimum at C if f of C is less than or equal to, very similar to the above definition, less than or equal to f of x for all x in I. And once again, f of C in this case is the absolute minimum. Now I say the, not an absolute minimum or a maximum. Here it's an indefinite article. This is the definite article, because if this is the highest point or the lowest point, there's only one y value. Now it could happen at a couple of places. So you could say f has a absolute minimum at 4, 5, and 27 or something, but the value at those points will have to be the same, because there is, that is the lowest y value, the least y value. So it is the absolute minimum. If you are asked to find the absolute minimum, that value is going to be the y value at that point. Okay, so I hope this is clear. And so again, we haven't talked about the differentiability. We don't need f to be differentiable. This is just a statement, the definition about any kind of function. In fact, f doesn't even have to be continuous. Okay, if f is like this, something like this, a step function, this is the highest y value, so that would be the absolute maximum, and this is the lowest point, so that would be the absolute minimum. Okay, so the function doesn't even have to be continuous. Okay, so do these exist? So here's the first set of definition. We define the absolute maximum and absolute minimum together are called absolute extremum. Okay, so do they exist? Okay, like I said, when you have a sine function, if f is sine of x, okay, the absolute maximum is 1. The absolute minimum is -1. And if somebody asks you, where does f have the absolute maximum, you can say at pi over 2 plus or minus 2k pi, or plus 2k pi. K can be negative. Okay. If somebody says where does the absolute minimum occur, you can say at negative pi over 2 plus 2k pi. So that's how you can describe that. Okay, no problem, right? Now I also mentioned when you have something like this, or on the entire line, these have no absolute maximum or minimum. Is it okay to say that? Yeah, if it goes to infinity, then you can't say, there's a maximum point or a minimum point, right? And even if it stops here, this is the, which example was it? Example number 5? Yeah, example number 5, where you have an open interval. Remember, at this point, both endpoints are not a part of the graph. That's why the point is missing, right? There's no absolute maximum or minimum, even though it gets closer and closer to 1. So again, those points, whether they are closed or open, make a huge difference. Okay, so keep that in mind as we go into the more advanced ideas of these, and we will decide how to find these. Okay, so the question of do these absolute maximum and minimum exist? Here is a partial answer. Okay, and this turns out to be a very important answer. So it's a theorem, which means it's a mathematical statement that has been proved, and therefore it is true, and it'll never be overturned, okay, even by the Supreme Court. Extreme value theorem, one of the crowning achievements of mathematical analysis. Extreme value theorem, EVT. What does it say here? If f is continuous, now continuity is a requirement. If f is continuous, I am so excited I can't even spell. Continuous on a closed and bounded interval. I will explain why it's important to say closed and bounded interval. Let's say I, which is A to B, including the endpoints. That's what makes it closed and bounded. Okay, then f has an absolute maximum and absolute minimum. Guaranteed. Okay, so the question, do they exist? So like, for instance, I said this has no maximum or minimum. It is continuous, but not on the closed interval, right? If you had a closed interval, if you had included -1 and +1, then this would have the absolute minimum of -1 and the absolute maximum of +1 if it were closed and bounded from -1 to +1. Now this is defined on all of the reals, and technically speaking, you probably don't know this, but the entire real line R is actually a closed set. Don't worry about that part, okay? But it's closed. It's also open, but don't worry about that either. But so that's why we have to have this word bounded, okay? If you bound this, like say from -1 to +1, then the function, the continuous function, has to have an absolute minimum and absolute maximum. This one does not, because the domain is not bounded, even though the function is continuous, okay? Oh, continuity is also important, essential, because continuity is essential, and the reason, I think it's easy to see, I can create a function that's not continuous on a closed and bounded interval from A to B that does not have an absolute maximum or minimum. Actually, think about this, okay? Create a function. Find a function defined on this closed and bounded interval from A to B, which does not have an absolute maximum or absolute minimum. Obviously, if it's continuous, this theorem guarantees the existence of an absolute max and absolute min, so this could not be continuous. But if you drop the requirement of continuity, maybe I should spell this out. Continuity is essential in here to guarantee the existence of an absolute extrema. The reason, try to find a counterexample. I'll come back to this, okay? There's an easy way to sort of draw a picture of this. Okay, so what about points like this? You know, aren't they max? Isn't this a maximum and this a minimum? And the answer is, well, no, not in absolute sense, right? This is not absolutely the highest point because the graph goes higher. This is not the absolute minimum because the graph goes lower. So then we will need a new definition to describe something like that. Basically, what we want to say is this is the highest point in close in the small neighborhood of it. Neighborhood, yeah, interval. Okay, this is a lowest point in a small interval around there, right? That's the whole idea. It's the idea of local or relative extrema. Maybe it's a good time to go back to this continuity. Or if you drop the continuity requirement, can you find a function, non-continuous function, defined on the closed and bounded interval from A to B, such that it has no absolute maximum or absolute minimum? And the answer is yes, you can do this, for instance. No, you don't want to do that one. Yeah, okay. So that function Well, actually, it's not defined at this middle point. So let's go ahead and define this. Okay. So this function, notice here, it gets closer and closer to this point, but never gets to that y value. So there is no maximum. And it gets down closer and closer to 0, but it never gets to 0 exactly. So there is no maximum or minimum for this discontinuous function, even though it's defined on the closed and bounded set I, right? So again, continuity is an important and essential element of the extreme value theorem. All right, going back to this new definition, we say f has a local, some people call this relative as opposed to absolute. Local is the better term, I think. A local maximum at C. If, now again, I'm trying to describe something like that. If there is an open interval, I stands for an interval, containing C, such that, ST means such that. I hope you know this by now, right? In mathematics, we use this a lot, such that, and abbreviate this as S dot T dot. And in fact, if you are like walking on the street or something, and if somebody uses phrases like such that, like, hey, let's walk to the store such that, whatever, that's probably a nerd mathematician talking. I can always spot these people, like when they're checking into the hotel or something, like, yeah. Oh, I want to check in such a way that I will be charged less. So what are you, a mathematician? Okay, so if f has a local maximum at C, if there is a small, even a very small open interval that contains C, such that fc is greater than or equal to f of x for all x on I. Okay, so the idea is this is a maximum point, a local maximum, even though it's not an absolute maximum, if you can find an open interval I so that along or on this interval I, this point is the maximum point. Okay, and the answer, that is the definition. Okay, so this point here, you can say this f has a local maximum at C, even though this is not a point of absolute maximum because the function continues to go up, right? So this happens to be a local maximum and not a, let me write this down. This is a local, C is where a local maximum occurs. Occurs at C, but not a not an absolute maximum, right? If you have a y is equal to x squared, this point is 0. Okay, so this y, you can say, has a local minimum, which is 0 at 0. Or can I say that? Can I say it's a local minimum here? That that y has a local minimum at 0? You say, no, you can't say that because f has an absolute minimum at 0. Okay, let me ask you this. Remember I said important, the definitions are super important in mathematics? Okay, so all you have to do, and the only thing you should do, is to check your statements against the definitions. All right, is this an absolute minimum? What's the definition? Absolute. This is an absolute minimum if this is the lowest point. If f of 0 is less than or equal to f of x for any x in the whole domain of this function, which is the set of all reals. And the answer is yes, right? This is definitely the lowest point. It is absolutely the lowest point. The least value of y occurs right here at 0. And that least value happens to be 0. So you could say, and it is correct to say, that this function has an absolute minimum, which is 0, at x is equal to 0. Okay, so the absolute minimum of y is 0, which occurs when x is equal to 0. Now, is this a local minimum? Okay, now don't be confused, or don't be under the impression that just because something is an absolute minimum, it can't be a local one. Okay, because the definition of a local minimum says this is a local minimum if you can find a small interval, including 0, where this is the lowest point, where f of c is less than or equal to f of x. And yes, you can find a small interval, like from -1 to +1, an open interval, in which this is the least point. So it is also a local minimum, right? Sorry, I didn't actually define the local minimum, right? You can picture, you can imagine what a local minimum is. F has a local or relative minimum at C if there is an open interval and it has to be an open interval for reasons which I'm not going to right here. That would be more advanced calculus. Open interval I containing C such that f of C is less than or equal to f of x for all x on that interval. Okay, so if this is a locally the lowest point or the least y value, then we say it's a local or relative minimum. A relative minimum or local minimum could also be an absolute minimum, okay, and vice versa. But it doesn't have to, they don't have to be. Okay? You can have like 15 local minimum values or 15 local minima, but then there's only one absolute minimum, which may or may not be there. Okay, so you can have a bunch of local minima and no absolute minima. That's also possible. All right, so I hope this is made it clear. Right? Make sure you go by the definitions. Again, I haven't said anything about differentiability, right? So I'm not saying these things only happen when the derivative is 0 or the tangent line is horizontal. I didn't say that, okay? So those may come later, but again, don't confuse the definitions with theorems that you may find later. Okay, so I was going to say something else here. A couple of things. When I talked about this open interval containing C, any open interval containing C is going to look like this, right? Right. And we have, and I use this word slightly in passing, but this is called a neighborhood. See, mathematicians, we want to be friendly, so we want to value our neighborhood. Any open interval containing C is called a neighborhood of C. Okay. In fact, in any open set, it doesn't have to be an interval, but for our purposes, an open interval would be okay. A neighborhood of C is any open set or an open interval containing C. Okay, so isn't that nice? I mean, this does look like a neighborhood, right? It's like if you live at C, then your neighborhood, consists of people that live around you. So that's a neighborhood of C. I hope you live in a good neighborhood. And the neighborhoods are really important for your absolute maximum and minimum. All right, so that's one thing. Now, this is strange, but I think I should tell you this. I wasn't going to do this, but I think it's important for you to know this. And this would sort of blow your mind, so be prepared to be shocked. All right, so here's what is this function? It looks like a constant function. Let's say y is equal to fx, which is 2 for all x. Okay, is there a maximum and minimum of this? No, of course not, right? Because look, I mean, it's like you can't find a highest point or the lowest point, or can you? Well, let's look at the definition. The definition says this random point, okay, this just x. Does f have a maximum local or relative or absolute maximum at this point? If let's say 10, okay. F has an absolute maximum at 10. Now, if you claim this, you are saying f of 10 is greater than or equal to f of x for all x, right? Is that true? Yeah, f of 10 is 2. And f of x at any point is 2. 2 is greater than or equal to each other, 2, right? So it is true. And again, I hate to say this, but you could say this constant function, f, has an absolute maximum at 10 and 9 and pi and -2 and -100. In fact, f has an absolute maximum at every single point. Yeah, that's sort of inconvenient, huh? Maybe you wouldn't like to hear that. But again, mathematically speaking, this would be a correct statement. And you say, wait a minute, does f then have an absolute minimum at any point? And the answer is yes, because at every one of these points, no matter what x is, f of, no matter what c is, f of c is going to be less than or equal to f of x for all x. So if f is constant, okay, that constant function, well, you could say any constant function has an absolute maximum and absolute minimum everywhere. And in fact, these are also local maximum and local minimum. Okay, so every point is a point of local maximum and absolute maximum and local minimum and absolute minimum, because you can always find a small interval in which, this is the f of c is less than or equal to f of x or greater than or equal to f of x. So for constant functions, these are sort of strange, but again, we have to go with definitions, and so that is a result of these definitions. All right, now the question, finding these points, finding local extrema, and that means local maxima or minima. And then later we will talk about finding absolute extrema. Okay, but those will be coming in the parts 2 and 3 of our video lecture for 4.3. So now you should probably take a break and come back for part 2.